Hello everybody, and welcome to our video on other convergence tests for series. So we're going to start by taking a look at what is called the alternating series test. So if the alternating series from n equals 1 to infinity of -1 to the n minus 1 power times b sub n, which is equal to b1 minus b2 plus b3 minus b4 plus ... satisfies the following conditions: that b sub n is decreasing, meaning b sub n plus 1 is always less than or equal to b sub n, and that the limit as n goes to infinity of b sub n is 0, then the series is convergent. So this is this is a rare case where we can actually just take the limit of a term to determine convergence, as long as we know that those terms are strictly decreasing and it's an alternating series. So that's one of the things we have to be careful about, is if these things aren't alternating series, we can't do this, but it does make checking convergence a whole lot easier for this particular type of case. So why does this test work? Well, the idea is this. Since I'm alternating between positive and negative terms, now mind you, I could have started with a negative term and went positive, so this could have been -1 to the nth power instead of n minus 1 power. The theorem would still apply exactly the same, so there's no actual meaningful difference there. I just didn't write the theorem twice to deal with both situations. But yeah, the terms could start negative and alternate to positive, or positive to negative. Either way is totally fine. It'll still be true. But why does this work? Well, we can basically sum up the idea in this picture. So if I am alternating between positive and negative values, then when I add my first term on the number line, I'm going to move all the way over to here. I'm going to add b1, and that puts me at the partial sum s1, which is the same thing as b1. Now s2 is b1 minus b2. So I'm going to go from there and subtract b2, and I'm going to end up here for my second partial sum. And then I'm going to add b3 for the third partial sum, and I end up here. And then I subtract b4, and I end up here. And you continue this back and forth and back and forth. And so what that tells you is, because each term is getting smaller and the terms are approaching 0, that you're going to essentially go back and forth narrowing down on some value, and that value will be the sum of the series. So let's take a look at an example, and in this example I'm also going to pull up a quick tool so that you can kind of see this in action. So the example we're looking at is the alternating harmonic series. So it's 1 minus 1/2 plus 1/3 minus 1/4 plus so forth and so on, and we write that series as the sum from n equals 1 to infinity of -1 to the n minus 1 power over n. So before we actually apply the test, I just want to use this as an example to show the idea I was trying to convey before. Hold on. It does not want to link. There we go. Okay, we'll zoom out here a little bit. So what I've got here, this value b is the sum that we were just discussing of the alternating series terms. And so this point A on the graph is the value of the sum. So wherever A is the value of the sum for that number of terms, capital A, that point. And so I'm changing, this slider here is how many terms I'm adding together. So the first term of this sum should be, hold on one second, that should be 1. Yeah, so the first term of this sum is 1, and so what do we get? 1. Now when I add my second term, I'm actually subtracting 1/2, so I get 1 minus 1/2, I end up at 1/2. And then I'm adding 1/3, and so I end up here, and then subtracting 1/4, and it goes back. And so as we add and subtract, you can see that point on the number line moving back and forth and narrowing in on a value. Now, we're not talking about this quite yet, but this should also give you an idea that we can use this to approximate values for sums by thinking about this distance that's being moved each time, right? Since each term is smaller than the term before it, my final sum has to be somewhere between those two terms. So we'll talk about that more precisely in a moment. Okay. Now, to go back to this problem, we want to test if this alternating harmonic series is convergent or divergent. And I think you can tell from the picture, or the tool we just looked at, that it's going to converge. But let's go ahead and actually show that explicitly. So b sub n plus 1, what's b sub n? Well, I'll rewrite the series slightly. B sub n is always the rest of the term inside the series that isn't the alternating portion. So in this case, b sub n is the 1 over n part. So b sub n plus 1 is 1 over n plus 1. And if I compare this to b sub n, which is 1 over n, of course, a smaller denominator is a bigger number. So b sub n plus 1 is always smaller than b sub n. So we've got that b sub n is decreasing. And the limit as n goes to infinity of b sub n is the limit as n goes to infinity of 1 over n, which is obviously 0. So this is an alternating series. We've satisfied both of the additional conditions. So that implies the series converges by the alternating series test. Okay, so let's take a look at another example. But we're going to just kind of throw in a little miniature fact mini theorem here. For an alternating series of this form, if the limit as n goes to infinity of b sub n is not 0, then the series diverges. So this is essentially just an extension of the test for divergence to be more specific about alternating series. So for alternating series, I don't have to check the limit of the whole expression inside. I can just check that limit of b sub n, and if it's not 0, then the series will diverge. So, for example 2, I see b sub n is 5n over 3n plus 1. And so if we take the limit as n goes to infinity of this, I'll take my usual approach and multiply by 1 over n, top and bottom. And this 1 over n term goes to 0, so I get left with 5/3. 5/3 is obviously not 0, so this implies the series diverges by the test for divergence. And you don't have to specify the test for divergence for alternating series, because really, if the b sub n portion is approaching anything other than 0, then the limit of the terms just doesn't exist, because it's going to alternate between getting close to two different values. And so by the test for divergence, the series will diverge. Okay. Another example, determine whether the series converges or diverges. What we need to show is that b sub n, which is equal to n cubed over n to the 4th plus 4, first thing we need to show is that this is decreasing. And in this case, the algebra will get really messy if we try to compare b sub n and b sub n plus 1. So instead of doing that, what we're going to do is find the related function and try to take the derivative, see if we can make that work. So let f of x be x cubed over x to the fourth plus 4. Then the derivative will be what? The derivative of x cubed, 3x squared, times the denominator, minus, that was supposed to be 3x squared, not 3x cubed, minus x cubed times the derivative of the denominator, that's 4x cubed plus nothing, all over the denominator squared. This is equal to 3x to the 6th plus 12x squared minus 4x cubed. That denominator was supposed to be squared. Man, I'm missing a lot of little things. Just making silly, writing silly things down. Okay, and yeah, that was supposed to be 4x to the 6th. I did it there too. So, this becomes what? 3x to the 6th minus 4x to the 6th is negative x to the 6th. This is 12x squared minus x to the 6th over x to the 4th plus 4 squared. And this is x squared times 12 minus x to the 4th. And x squared is positive. X to the 4th plus 4 squared is positive. So when is this thing negative? So this is negative for 12 minus x to the 4th being negative. Whenever 12x minus x to the 4th is negative, the whole thing will be negative. So whenever x to the 4th is greater than 12. And when x is 2, 2 to the 4th is going to be 16. So this is true for any x greater than 2. And that's good enough, as long as I've got, just like with the integral test, some place where this is decreasing onward, we can still apply this alternating series test. So that implies that b sub n is decreasing, so we've got that part. And if we take the limit as n goes to infinity of n cubed over n to the 4th plus 4, I can rewrite this my usual way as the limit of 1 over n over 1 plus 4 over n. And so these two terms both go to 0. And so my whole limit is 0 over 1, which is 0. So this implies the series converges by the alternating series theorem. All right, let's go ahead and move on. So now we can consider the alternating series estimation theorem. So this theorem says if S is an alternating series that is convergent, then the error cap R sub n of using the partial sum S sub n to estimate the series S satisfies that the error R sub n is equal to the difference between the actual sum and the partial sum, which will be less than the n plus 1th term. So what do I mean here? Well, what we saw, if we take a look at our number line here, so from 0 to, we'll say 1 here, when we were looking at our partial sum for the alternating harmonic series, we saw, okay, we had this first partial sum, and then we subtracted b2, and we end up here at the second partial sum. And then we added b3, so we end up here in the third partial sum. And so what we're saying is somewhere in here is the actual value of the sum, and the distance here is the error between the partial sum and the actual value of the sum. And what we know is b sub 4 is going to take me back, and it's going to go past the actual sum. So what we're saying here is that the error, the absolute value of the error, is less than or equal to the value of the n plus 1th term. Okay, so let's put this to place to actually approximate a sum of a series correct to 3 decimal places. So before we get started, when I say correct to 3 decimal places, I don't mean less than 0.001. That's not what we mean. I shouldn't have said x. I don't mean that my sum is accurate to that, or my error is accurate to that. What I mean is that my error is less than 0.0005. And the reason for that is that if the error is less than 0.0005, I won't round any digits in the 3rd decimal place. So when I say correct to 3 decimal places, I go that extra decimal place out and put a 5 so that there's no rounding error that gets accumulated on the 3rd decimal place. Okay, so with that in mind, let's go ahead and try to tackle this. So what is b sub n? It's 1 over n factorial. And 1 over n factorial is clearly bigger than 1 over n plus 1 factorial. I'm multiplying by an extra number in this factorial, so the denominator is bigger, so the whole thing's smaller. And also the limit as n goes to infinity of 1 over n factorial is 0. So this implies the series converges by the alternating series test. So now, if I want to find the sum of the series correct to 3 decimal places, I have to figure out how many terms I need. So I need to start writing out some of those terms. Now notice a little detail here. This sum is starting with n equals 0. So I'm going to start out by writing the b sub 0 term, which is 1 over 0 factorial, which is 1 over 1, which is 1. And b sub 1, that's 1 over 1 factorial, which is also 1. And b sub 2, that's 1 over 2 factorial, which is 1/2. Now, you might think to yourself, can't I solve algebraically to figure out when b sub n plus 1 will be smaller than 0.0005? Oftentimes you can, but in this case you can't, because we don't have any good algebraic tools to work with the factorial. So in this case, we just have to kind of brute force the problem. So we get 1 over 3 factorial, and 3 factorial is 6. 3 times 2 times 1 is 6. And I'm going to just keep going down this list. B sub 4, that's going to be 1 over 4 factorial, which is 4 factorial is the same thing as 3 factorial times 4. So this is 1 over 24. And b sub 5 is the 24 times 5 in the denominator, so that's 1 over 120. Now, real quick, I'm going to go up here and just convert this expression to a decimal. This is 10, 100,000, 10 thousandths place. So this is 5 over 10,000, which is 1 over 2,000. So that's what I'm looking for, a fraction that's less than 1 over 2,000. All right, b sub 6 is going to be, well, the 120 is going to get multiplied by 6 now. And so that's going to be 720. So 1 over 720. And so b sub 7, that 720 is going to get multiplied by 7. But that's kind of where my ability to do these in my head falls apart. So let's plug that into a calculator, times 7, and we get 1 over 5,040, which is certainly less than 1 over 2,000. So here's the key thing, what I want to be clear about, and it's a really common mistake, and it's a really minor thing, but it is conceptual, and we want to make sure that students understand conceptually what's happening here. This term, why did it do that? Let me find my place again. Where did we go? This term, b sub 7, is b sub n plus 1. That's b sub n plus 1. And remember, our error, r sub n, corresponds to taking the sum of n terms, the nth up through the nth term. We don't include the b sub n plus 1 term. That just tells us what the error, the maximum error is. So this is b sub n plus 1. So what I'm going to do is add up all the terms before. But remember, when looking at b sub n, we weren't considering the fact that these terms are alternating. So we start when n equals 0 with the positive term. So my sum up to the 6th term starts with my 0 term, which is positive, minus 1, the b sub 1 term, plus 1/2, minus 1/6, plus 1 over 24, minus 1 over 120, plus 1 over 720. So the 1 minus 1 cancels, which is nice. And now we've got the rest of this expression here to finish evaluating. So we'll just throw that into a calculator real quick. And we get, I should say, approximately 0.368. So this is a really nice tool because it gives us a way to guarantee that we can approximate this type of series within a pretty reasonable value, and it doesn't take that many terms to do so. What that means is that it's not very computationally expensive. So if you're using a computer to approximate certain types of series, it can often be really easy for the computer to approximate it very accurately in a way that, of course, by hand we wouldn't want to do. But we do practice doing some of these by hand so that we really understand algorithmically what's happening here when we try to apply this alternating series estimation theorem. Okay, so let's take a look at another example. This one is going to be slightly different. We're just asking how many terms are needed to estimate the value of the sum correct to 5 decimal places. So I'm not going to actually compute the sum correct to 5 decimal places, and you'll see why when we get there. We're just going to take a look at how many terms would be needed to get this series accurate to 5 decimal places. So, of course, 5 decimal places means less than 0.000005. And as a fraction, that would be 5 over, that's 10, 100,000, 10,000, 100,000, a million. It's 5 over 1 million, which is 1 over 200,000. So b sub n plus 1 is 1 over n plus 1 squared. And in this case, I'm just going to say, hey, this series converges. In general, I would expect students to show that when they are applying the alternating series estimation theorem. So I would expect you to do that. It's very simple in this case, but for time, I'm going to cut that out since we already did a couple examples of that. So here, we're just going to do just the part where we actually compute how many terms we need. So b sub n plus 1 is 1 over n plus 1 squared, and I want this to be less than 1 over 200,000. So if I multiply both of these expressions across that inequality, that gives me that 200,000 should be less than n plus 1 squared. And if I take the square root, that's the square root of 200,000 is less than n plus 1. And technically, I should put a plus or minus here. But of course, I'm not going to have a negative number of terms. So it doesn't make any sense to include the negative answer here. We can exclude that one. And now we can subtract the 1. And we get that n has to be greater than the square root of 200,000 minus 1. So if we plug that into a calculator, let's see what we get. So we've got the square root of 200,000 minus 1. We get 446.2. So n has to be greater than that. But n also has to be an integer. So since it has to be bigger than this, n needs to be at least 447. So we need 447 terms in order to find this series accurate to 5 decimal places. So of course, this example illustrates why when it comes to actually approximating these series, you definitely want to use a computer for a lot of them, but we can at least pretty easily find out what the number of terms we need so that we don't necessarily spend extra computational power on doing these sort of calculations. Okay, let's go ahead and move on to the definition for an absolutely convergent series. So a series is called absolutely convergent if the series of absolute values, the sum of the absolute value of a sub n, is convergent. So we're going to show that the sum from n equals 1 to infinity of negative 1 to the n minus 1 power over n squared is absolutely convergent. And so the way we do that is by just considering the series of its absolute value terms. And since we're taking the absolute value, the only difference that happens with this numerator is it alternates between negative 1 and positive 1 normally, but if I take the absolute value, my numerator is always going to be positive 1. So this series will be the same as the series 1 over n squared, which is a p-series with p equal to 2, which implies it converges. And that implies that the original series from n equals 1 to infinity of negative 1 to the n minus 1 power over n squared is absolutely convergent. All right, so that was a nice, easy one. Let's move on. Now, a series, on the other hand, is called conditionally convergent if it is convergent, but not absolutely convergent. So here we've got the alternating harmonic series. So we already showed earlier that this series converges, right? So that was example 1. The alternating harmonic series. So let's go back to here. So we showed it converges in example 1. But when we take the absolute value of its terms, so from n equals 1 to infinity of negative 1 to the n minus 1 over n, so we take the absolute value, that's the sum from n equals 1 to infinity of 1 over n, which is the harmonic series. And we've, of course, proven that that diverges. So we've already showed that the series converges And we've now shown that when we take the absolute value of its terms, it diverges, which again, we've shown that in a previous section as well. And those are the only two things we need to show that the series is conditionally convergent. All right. On to the next one. So now we've got a theorem, and this is a very useful theorem. This is the absolute convergence theorem. And it says that if a series of terms a sub n is absolutely convergent, then it is normally convergent. Now this only goes the one direction though. A series being convergent doesn't show absolute convergence, like we saw here. This series converges, but that doesn't imply absolute convergence. However, if it's absolutely convergent, then it is convergent. Then the original series is convergent. So how do we show that? Well, first, we note that if I take a sub n plus the absolute value of a sub n, I'm either going to get 0 or 2 times the absolute value of a sub n. So if a sub n is negative, these will cancel out and give you 0. If a sub n is positive, they'll add together and give you 2 times the absolute value of a sub n. And so we get this inequality, that a sub n plus the absolute value of a sub n is between 0 and 2 times the absolute value of a sub n. So since we're assuming that the series converges absolutely, then a constant multiple of the series is also convergent, and therefore the series of a sub n plus the absolute value of a sub n is convergent by the comparison test. Now, since we can always rewrite the sum a sub n as the sum of a sub n plus the absolute value of a sub n minus the sum of the absolute value of a sub n, as long as these are both convergent, which we just showed, right? We have that this series is convergent. We showed that this series is convergent, and this is the difference between two convergent series. Then that means the original series is convergent. So, taking a look at example 8, let's determine whether the series is convergent or divergent. So I see the sine of n over n cubed, and this is tough because I would like to do a comparison, but sine of n over n cubed is not strictly positive, so I can't do a comparison directly. So what can I do? Well, in this case, I can instead consider the sum from n equals 1 to infinity of the absolute value of sine of n over n cubed. And since n is positive, I can rewrite this as the sum from n equals 1 to infinity of the absolute value of sine of n over the normal old n cubed. And now, when we look at the absolute value of sine of n over n cubed, this must be positive. And sine is bounded by 1, so it's less than or equal to 1 over n cubed. So then, since we know that the sum from n equals 1 to infinity of 1 over n cubed is a p-series, it converges since p is 3, which is greater than 1, and that implies this series from n equals 1 to infinity of the absolute value of sine of n over n cubed converges by the comparison test and that implies that the original series converges by the absolute value, or the absolute convergence theorem. Okay, well that's it for that one. Whew. Let's see, what do we have next? So next we have the ratio test. And the ratio test is another test that's going to be super, super important. And it's going to seem really, really, let's say, overly strong. Like, why did we learn all these other tests when this ratio test does all this stuff? But that's why one of the reasons why this is one of the last tests that we learn, so that you don't become overly reliant on it. And that's going to be the third part of the theorem, is why we can't become overly reliant on this test. So the ratio test says, consider the series from n equals 1 to infinity of a sub n. If the limit as n goes to infinity of a sub n plus 1 over a sub n's absolute value is L, some number which is less than 1, then the series is absolutely convergent. If this limit is greater than 1, or infinity, then the series is divergent. But if the limit is equal to 1, the test is inconclusive. It tells you absolutely nothing. So this is sort of the key issue here. We're going to deal with, in our later sections, a bunch of cases where the ratio test ends up inconclusive. And so we have to fall back on all of those previous tests that we've learned, even though the ratio test is very useful, and for the most part, not too hard to do. So we want to take the limit of the ratio of a sub n plus 1 over a sub n. So the first thing I'm always going to do with these problems is deal with the a sub n plus 1 over a sub n part. I'm going to write it out and simplify it before I go to take my limit. And so for a sub n plus 1, all I do is everywhere I have an n, I'm just going to plug in n plus 1 instead. So this will be n plus 1 to the 4th power over 5 to the n plus 1 power over negative 1 to the n power times n to the 4th over 5 to the n. So that's step 1. And step 2, I'm going to multiply by the reciprocal. We've got negative 1 to the n plus 1 times n plus 1 to the 4th over 5 to the n plus 1 power times 5 to the n power over negative 1 to the n power times n to the 4th power. And so now I'm going to do a bit of simplification. So here I've got negative 1 to the n plus 1 over negative 1 to the nth power. That leaves me with just negative 1 up top. And 5 to the n over 5 to the n plus 1 leaves me with a single factor of 5 in the denominator. So this is negative 1 over 5 times, and n plus 1 to the 4th divided by n to the 4th can be written as n plus 1 over n all to the 4th. Now if I take my absolute value, the absolute value of negative 1 is 1, so I get 1/5 times n plus 1 over n to the 4th. And so now I can compute my limit. My limit as n goes to infinity of a sub n plus 1 over a sub n is just the limit as n goes to infinity of 1/5 times n plus 1 over n to the 4th. And I can pull my constant out of my limit. And also, if I have a quote-unquote x to the 4th, this is treated as a continuous function. I can move that limit inside. And so we get the limit as n goes to infinity of n plus 1 over n to the 4th. And at this point, we've done a whole bunch of these types of limits. It should be pretty clear that this limit is going to be 1. And so this is 1/5 times 1 to the 4th, which is 1/5. And finally, that is less than 1. So this implies by the ratio test the series converges. Okay, that's it for that example. So now, example 10, we're going to test the convergence of the series from n equals 1 to infinity of n to the nth power divided by n factorial. And so again, we're going to use the ratio test. So we're going to set up a sub n plus 1 over a sub n. That's the absolute value of n plus 1 to the n plus 1 power divided by n plus 1 factorial divided by n to the n power over n factorial. And now we've got to start rewriting this expression a bit. So what I'm going to do here, well, first I'm going to rewrite this as multiplying by the reciprocal instead. That's n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. And now we'll start rewriting this. So I'd like both of these expressions to have n to the, or have b to the nth power, so I can combine them. So this first expression, I'm going to pull a factor of n plus 1 out. So then I get n plus 1 times n plus 1 to the nth power times n factorial over n to the nth power. And in my denominator, that's a factorial expression, n plus 1, which is the same thing as n plus 1 times n factorial. So now I can do some simplification. N plus 1 over n plus 1 cancels, n factorial and n factorial cancels. And then this becomes the sum of n plus 1 to the n over n to the n, which is n plus 1 over n to the nth power. Now, all of these terms are positive, so this is just the sum of n plus 1 over n to the nth power, which is 1 plus 1 over n to the n. So now when I go to take my limit, this is the limit as n goes to infinity of 1 plus 1 over n to the nth power. And you may or may not recall that this limit is the definition for e, the number e. So if you know that, rather than computing this the long way, I'm totally fine with a student just saying, hey, that's e. I know what e is. Now, the alternative approach here is to rewrite this expression as the limit as n goes to infinity of e to the ln of 1 plus 1 over n to the nth power, move the n in front, and then rewrite this expression and apply L'Hopital's rule, blah, blah, blah. It's a pretty long process. So definitely knowing that this limit is e can save you some time, and I'm going to leave that like that. I've done examples like this in Calc 1 though, so if you wanted to go back and say, look at problems from L'Hopital's rule, you can definitely find them there. All right. Oh, well, we didn't actually state our conclusion. E is bigger than 1, so this implies the series diverges for, or by, I should say, the ratio test. Okay, and now we'll take a look at the root test. That'll be our last test for this section. And the root test is very similar to the ratio test. It says consider the series from n equals 1 to infinity of a sub n. If the limit as n goes to infinity of the nth root of the absolute value of a sub n is L, which is less than 1, then the series is absolutely convergent. If the limit as n goes to infinity of the nth root of the absolute value of a sub n is bigger than 1, the series is divergent. And if the limit of the nth root of the absolute value of a sub n is 1, the test is inconclusive. So key fact here is that if either the ratio or root test is inconclusive for a series, the other will be as well. So what I mean is, if you try the ratio test and you get 1, don't waste your time trying the root test. It's not going to help you. Likewise, if you try the root test and you get 1, don't waste your time on the ratio test. It's not going to help you. You have to go back to our previous techniques to figure out how to test that series for convergence. Okay, so now we'll take a look at an example where the ratio or the root test is appropriate. Really, the root test, in my experience, almost never is easier than the ratio test. The ratio test, the algebra almost always works out easier, except in the very specific circumstances where your terms are all raised to the power of n, or something very similar to that. So maybe if it looks like all your terms or most of your terms are raised to the power n, you should consider the root test. Otherwise, I wouldn't bother. Most of the time, the ratio test will work out better. But again, sometimes it happens. So if we take a look at the nth root of the absolute value of a sub n, that's the nth root of 4n plus 5 over 7n plus 2, which in that case, the nth root and the nth power cancel. Now notice, I didn't write the absolute value here because these terms are strictly positive. So I don't need it in this case. I do have to worry about that in other problems. But the nth root and nth power cancel, and so I get 4n plus 5 over 7n plus 2. So that simplifies really nicely. So now if I go to take the limit as n goes to infinity of this nth root of the absolute value of a sub n, I'm really taking the limit of 4n plus 5 over 7n plus 2. And again, we would multiply by 1 over n on the top and the bottom, yada, yada, yada. We've done a bunch of these at this point. That limit is 4/7, which is less than 1, which implies the series converges by the root test. Okay, well, that's it for this section, so thank you for watching.